Okay, let's start with this next talk on day 2. It's about full disk encryption, so just to enable you to make sure nobody gets a peek on your hard drive if this hard drive will ever disappear. Our next speaker is Jürgen Pabel from Cologne, and he will give you an introduction into the necessary tools for both Windows and Linux. Welcome him, please.
Okay, so thank you and welcome everyone. Let me introduce myself first, and I'll tell you why this is important to this talk. Well, I studied in America, so this is why my English is the way it is. If you have any issues with it, raise your hand, yell at me, whatever. Make yourself heard. The second part is I work as a security consultant, so my look on this is more often than not through the eyes of an enterprise. Not necessarily as a hacker. Sometimes it is, sometimes it's not. So you'll see that. And the last part is I like to play rugby, but nowadays not so much as I used to. And why is that important? It's important because I have a free polo shirt to give away. And all right, if no one gets the question, you get it. What are we looking at and why are we looking at it? So the first question is, does anyone recognize this movie quote? Okay, no one. How long is it going to take until someone Googles it? What's the movie? Can anyone tell me? What is it? No? Nope. Nope. All right, Google time now. Anyone? Nobody wants a free t-shirt? Nope. Okay, I have a backup question for that later on. It's Mystery Science Theater 3000. Okay, so we're looking at full disk encryption, and there's two ways you can do that. One is in hardware, and that's really pretty much a new thing, where you have a little device like inside your hard drive that encrypts it, and you pretty much don't ever see anything of the encryption. Or you can have a software solution that you install on your operating system or just make use of, and that encrypts your data on the CPU and sends it encrypted to the disk. So the disk doesn't know anything about it being encrypted, in contrast to the first one. Why we're looking at it is because data is at risk. Laptop theft is a pretty big issue in most corporations, and I believe in the future there's also going to be more of full disk encryption in desktops. Oops, that was wrong. Desktops and server systems in order to minimize the data lifetime in terms of when a server goes out of order, you don't have to worry about destructing the data. You just make sure the key is destroyed. So that's why we're looking at it. And what it does, like I said, it encrypts pretty much every bit on your hard disk. And that's sort of a odd thing, because full disk encryption, the name says the disk is fully encrypted, but you can encrypt disk partially, and the name really only is supposed to say that you're working on or with an encryption solution on the disk layer. You're not working with an encryption solution working in terms of like an encrypted archive or in terms of like application encrypted file. So you're working at the disk layer, and you don't have to worry about individual files. So, like I said, through hardware, and these are just the few notes that I'll go into in terms of hardware, because the software side is much more interesting. I'm sure you've all seen the USB controllers that have supposedly encryption controllers in them, and some of them are good, some of them aren't. That's just one form of how disk encryption can be done. Another one is the hard drive itself, an internal hard drive providing an encryption. And I believe there are two right now, Seagate and Toshiba, that offer this. And the way it works is the drive just offers the ATA security command that usual drives also offer, but only at a functional level. With usually drives that offer these, you can take out the platters and you can extract the information. With these specific products, you need to use the ATA security commands, provide a password, and the password is actually used to derive the encryption key. So it's much better security, cryptographic security than just a functional ATA security command for your hard drive. And then through software. The operating system provides this because it needs to work for all applications that you want to use, so it's transparent. You just have to install it, configure it, whatever, and there it goes. And hopefully it doesn't impact your everyday performance too much, because CPUs are pretty fast nowadays, and even on somewhat older systems, you don't really get impacted that much performance-wise. So, architecture, pre-boot authentication. When you have something that's encrypted, you usually expect that you have to supply something so you can decrypt it. And if the software is an operating system component and encrypts the disk, then the operating system is likely to be encrypted itself also, which means you need to supply a secret in order to unlock the disk, in order to start the operating system. And this pre-boot authentication environment does just that. It gets loaded by the BIOS from unencrypted storage. In most cases, this will be your MBR on your hard drive and some other area, because the MBR is not big enough. So with Linux, it's a little bit different. You have usually you have an unencrypted boot partition that holds your kernel, your init RAM disk, and this partition contains the logic to display a prompt to get the password, to ask you to insert your smart card, whatever. So this is sort of not really a pre-boot authentication by like implementation, but if you want to be real specific about it, but it's sort of that. In Windows, it's more like that, because in Windows, the architecture is different, and you have a proprietary pre-boot environment that does just that. It displays a prompt, takes your password, whatever, and then sets up the system so it can continue to boot. And yeah, I already said that. So the next step is to boot the operating system. With Linux, like I said, it's a little bit different. All it has to do is, once you have the password, is mount the file system that's being encrypted, and the initialization phase goes on as usual. With Windows, it's a little bit different, because the operating system with the Windows kernel or the NT loader, who here knows what the NT loader is? Hands up, please. Okay, so when you start Windows, that little black screen with the little bar scrolling, that's not actually Windows yet, it's the NT loader. What that does is it really loads the NT kernel, and this little loader, of course, needs to get loaded also. So the way the encryption products do it is they use a function, the NT loader uses a BIOS function to load data from the disk. So it says, hello, interrupt 13, please give me these bytes from the disk over here. And what these full disk encryption products do is they hook the interrupt routine, and they extend it with the encryption and decryption logic. So when you when the NT loader is run, it uses interrupt 13, and because the pre-boot environment has already replaced the in13 function or extended it, NT loader loads the data from the disk, which is encrypted, but it does so transparently. Did I get this point across? Okay. So when Windows has started, it needs to access the disk and do the encryption. The way applications sort of look at it is they just write to the file system, just nothing different about it. The operating system kernel has a little component that is the full disk encryption driver that actually intercepts the data before it gets sent to the disk and encrypts it and then sends it to the disk in encrypted form. So for Linux, there's a couple solutions that do this. One is the device mapper, which is an architectural solution. It essentially allows you to use a different device than your hard disk, and this device does nothing but encrypt the data and then pass it on to the real device driver. You can also do device driver hooking, which is more of a kernel module that looks at the driver for the hardware for the disk and finds the right point and just reroutes the function call to itself, does the little encryption magic, and then passes back on to the driver. So it's more of a hook and inject sort of solution rather than device mapper, which is an architectural. In Windows, you have lower level filter drivers, and what these are is every Windows driver has a higher and a lower level filter driver, which is sort of a callback mechanism. It allows you to, filter stuff, to work around bugs maybe in the lower level filter driver, and the lower level filter driver is also used to encrypt and decrypt the data to and from the hard disk. So when we look at the boot process, the NT loader uses the N13 to load the data from the disk, and the interrupt routine takes care of the encryption decryption. Well, actually pretty much just decryption on booting. So the Windows encryption driver then needs to do the same work, and since it doesn't use the interrupt routine anymore because it's just much too slow, it needs to somehow obtain the cryptographic key so that it can just do the work inside its driver and be much more efficient than the N13 implementation. And this is called the key handoff. So several products, or pretty much every product, has a little different strategy to this. TrueCrypt, for example, which is an open source full disk encryption solution, and another, they sort of search for the key. They don't know where it is, but they search for it, and if they locate it by some magic bytes, then they say, okay, I found it, let's go. Commercial products usually have a dedicated memory location where they put it, and the driver just knows, okay, it's there, I'll take it. When you're talking about disk encryption, you either consider this when you set up the system, so during installation it's encrypted, or you want to add it later on. So there's the aspect of initial encryption. How do you transfer your disk from being unencrypted to being encrypted? On Linux, you have like I said, the device mapper, and one drawback to it is that you cannot convert an existing file system in place yet into an encrypted file system. So you have to pretty much set up a new file system. Of course, you can just write a new file system over the device mapper onto a new disk and copy your files over. There are several workarounds, but you cannot just transparently install some or tweak some configuration and then your system will be encrypted after a while. There are commercial products also for Linux that use the device driver hooking, and they can transparently encrypt your hard disk as sort of an installation step. So the way they do it is they just inject their code into the driver and process all the sectors on the disk and remember which ones were encrypted, which ones haven't been, and just continue to encrypt the whole disk until it's done, and then it just continues in regular mode, just doing any encryption and decryption as necessary on reading and writing. So in Windows, the device driver pretty much is implemented like a device driver hooking in Linux through the lower level filter driver, and the in-place on-the-fly disk encryption is a standard feature in Windows. Windows users would not take, okay, you have to reinstall Windows in order to get disk encryption. They just won't accept that. So, and they shouldn't. So, if you look at this, once the disk is fully encrypted, you're all set and your data is secure more or less. So let's look at what solutions we have on the market that are first for Windows and that are commercial. There's the CompuSec. This is sort of a lesser known, and I don't know really how good it is. I've tried it a few times. I've had some issues with it, but there's two big bonus points. For one, it's free, as in it doesn't cost any money, and there's a Linux version available for you. So it might be worth checking out. Checkpoint has a product that has an interesting part. It's the only full disk encryption solution that's available for Mac OS. So if you're looking at full disk encryption on Mac, this is right now the only way you can go. You can use a solution that comes with Mac OS that encrypts your user directory, but that's a different story. So PGP has one, and I don't know anything interesting to say about this one. SafeNet has a protect drive, and before the name was SafeNet, it was Safe Boot or something. This is an interesting product to look at. It has a few quirks, and there are some options that I don't know what to make of in terms of like security. But much more interesting is the security finally secure. And it's interesting because its pre-boot authentication environment is actually a Linux-based environment. So what they do is they install a little Linux environment on a newly created partition. This boots, it displays you a little prompt for entering your password or sliding in your smart card, and takes the cryptographic material and then actually just then it hooks the in13, and then it just passes on control to the NT loader to start Windows. So Ultimaco Safeguard is, to my knowledge, the first commercial product that's been available to sort of the Microsoft operating systems. And the last one is Windows BitLocker. That's interesting. Windows BitLocker is interesting because it has a specific feature that we'll get to in a moment that no other product has. So the other solutions for Windows open source, I'm sure everyone has heard of TrueCrypt. TrueCrypt is pretty much the reference open source implementation for full disk encryption. And what I personally found is TrueCrypt is a great product, but it has quite a few issues in terms of like internally, but also on the front end, and we'll get to these also. There's another lesser known project that's called Descriptor, and this is actually a project that I've been involved with a little this year, and I'll also get to that in a moment. Then we have the Linux. I've also already said there's the device, or actually there's encrypted file system on, or file systems on encrypted devices. There's the Lux, the encrypt. This is the device mapper. Lux is actually the Linux unified key setup or something. It just defines sort of like the specification for the on-disk layout, and the encrypt is sort of the kernel driver glue that makes it all work. We have cryptographic file systems that file systems themselves implement disk encryption, and we don't really want to look at these right now because they're standard file systems, so to say. And then there's the stack file systems that you can use to overlay one file system over another, and the encryption takes place at that level, and neither the file system nor the disk nor anyone else knows about the encryption. So, and that's only for completeness right now. So what are the risks when you use a disk encryption product? How many of you have been to the cold boot yesterday? All right. Everything that was said there is correct, but there's sort of, you have to look at it like, what is your risk? You're really only at risk for this when someone gets a hold of your system that's running, or when someone has been running until very recently, or when it's being able to be made runnable. So when you don't have to supply a cryptographic token in order to boot it up, then you're at risk for a cold boot attack. But you're also at risk to other stuff, like if you have a system that has a network card and the network stack is enabled, you're at risk to being attacked over a network. So full disk encryption does nothing to mitigate that risk. So, but the prime risk, the number one risk, is weak passwords. I know this crowd is a little different than other crowds, so usually people think, okay, 8-character passwords are pretty safe, and it's established that this is sort of the minimum for corporate environments. But if you look at encryption, a password character only gives you about 6 bits of entropy, so randomness. And this is really if you use uppercase, lowercase, digits, and some special characters. If you use less to create your password, then it's less. So if you want to protect a 128 or 256-bit cryptographic key, you would have to use like a 35, 40 character long password. And obviously in a corporate environment, no one will do that. So weak passwords are a significant threat to data being stored on an encrypted hard drive, at least for the software implementations. So the cold boot attacks are listed at number 2 because, as I said, it requires a powered-on computer system. And if you look at the global threat scope, that's really just a minor threat. Coercion is also interesting because if you want to go into the US Customs might ask you to open your computer, provide your password, and they look at whatever data you have. So they can force you to provide your password. They may say, okay, you rejected entry to the United States. They may detain you. They might have ways for you to supply your password. Of course, there are other scenarios where this might be even more threatening, like in criminal environments, they may pose a threat to your health. And you think twice whether your health is more important or your password. So coercion is a risk, and the only way that you can sort of guard yourself against that is sort of by obscurity. If your opponent doesn't even know that you have something to hide, then they won't know what they need to look for. So there's a feature that TrueCrypt implements, which is called hidden operating system, that we'll get to in a minute. And if you have something hidden to a point where you can provide whatever opponent a password that they can open your computer, look at, find nothing suspicious, and if they don't know that there's something more, then they'll be satisfied with that. So there's a few oddities that I found in my work. Number one is TPM support is not TPM support. TPM modules allow you to, or you would expect to use a TPM chip so that you can store your cryptographic key in it. And this is actually the one thing why Windows Vista BitLocker was mentioned, is because it's the only full disk encryption product out there, at least for Windows, that allows you to store your cryptographic key in the TPM. All the other products, they have TPM support, but when you ask them, they're using the TPM to bind the operating system to the TPM chip. So what they do is they boot the operating system, and when you log in, the login function does one more check. It not only checks your password, but it also checks whether the TPM chip is the same TPM chip that was present when the system was installed. So it has no influence on the cryptographic setup. And that was significant realization we've made. We've had several vendors out there, and they all said, yeah, we have TPM support, and when you drill down, they all just sort of drill back and say, well, we can work on this. And there's actually one vendor that'll implement the cryptographic key storage on the TPM chip next year. The reason why they don't have it implemented is also fairly trivial, because TPM chips are vendor-specific, proprietary devices pretty much, and they you need to know what protocol to talk to each model and make of a TPM chip, and they don't want to do that. So they want to, if they say we need TPM support, they want a TPM support for everybody, and there's a well-defined interface on Windows, Windows DLL, that every TPM manufacturer adheres to. So they just take the easy implementation route and implement the wrong thing. Another thing we noticed was multi-disk setup, and I'm not talking about RAID here. So we're talking about a C drive and a D drive. You want to encrypt both disks, and pretty much all the products support this, but pretty much all the products fail when you actually have a disk failing. So there's pretty much not a single product out there that allows you to run a system with two disks. And I'm talking about internal disks. I'm not talking about USB drives or anything. So you got to expect some failure at some point from one of the disks, and all these products fail. And when such a failure occurs, all the products have to be deinstalled, which means decrypting your encrypted system, which means removing the software, which means reinstalling, which means re-encrypting all drives. And that's just a major flaw when you look at 20,000 systems that have multiple disks, and you want to install a full disk encryption software on there. RAID is a sort of different story, because RAID sort of abstracts the multiple disk setup to the cryptographic component. So if your product that you choose has RAID support, then very likely you'll be okay with RAID failures. So now we go into a little segment that focuses on open source, TrueCrypt. It has unique cryptographic features. I've already mentioned hidden operating system support. It's also pretty much the only full disk encryption product out there that sort of has its on-disk layout set up so that you cannot deduce that there is encrypted data on it. So if you don't have anything pointing to that there is data on it, you won't know that there is data on it. You won't be able to prove it. It's multi-platform compatible, runs on Linux and OS X and whatever else. But it's unsuitable for most enterprise environments because there's no key management. TrueCrypt, you can specify a password, encrypt your hard disk, fine, but when you're an admin, you need recoverability, and you cannot do that with TrueCrypt just yet. You also are not likely to be able to do that with TrueCrypt because the TrueCrypt specifications don't provide for that. There's no user management, so you have a single password for your encrypted disk. If you have multiple users using it, you need to use the same password and give it to both users. So it's very technical, and the user interface is sort of not streamlined. How many of you have used TrueCrypt for disk encryption? Okay. How many of you, without using the manual or reading an introduction, after the installation, knew what to do to encrypt the disk? All right, see? So significantly less. Now expect if I ask the same sort of question in an audience where I was introducing this TrueCrypt as a corporate full disk encryption solution. People will be just confused. So this cryptor is another open source project that implements the TrueCrypt specifications. It was created by some Russian guys, and it's still in development. The current version is 0.4, and as I said, it implements the TrueCrypt specifications, so it's TrueCrypt compatible. You can use this cryptor to encrypt your disk, and then use some TrueCrypt recovery tool later on to, to open your disk if you have the password to do whatever recovery work you need to do. Sadly, and this is one big point, this cryptor decided to go away from the TrueCrypt compatibility for some reasons that I don't understand. Or I do understand, but I don't agree with. They just make it a little bit easier on themselves, so TrueCrypt won't be compatible anymore. It's also unsuitable for enterprise environments because it also doesn't have key management, because that's just lacking in the TrueCrypt specifications. There's no user management, and it has no installer application. So if you want to use this cryptor from the project website, you have to take the system driver, you have to copy it pretty much to where you need it to. You need to run some commands to set it up, and it's just, hackers can do it, but no one else, pretty much. So this is pretty much the reason why I got involved, and I created a little derivative. Right now it's called +AC, based on this cryptor. And the one point, it includes an installer and uninstaller. So you're guided through the installation to the point where you say, which drive do you want to encrypt? What's your password you want to use? Okay, let me go encrypt the disk, and you pretty much, you can give this your mother and she'll know what to do. We've also written some manuals, so that might be of some help for some. But because this cryptor itself decided to go away from TrueCrypt, we'll probably fork this under a new name. This cryptor +AC isn't really that sexy of a name, so we'll see where this goes. I've talked about the TrueCrypt specifications, and here's a little more detail about this. So there's a volume header. When you have your disk drive and you want to encrypt it, there's a header somewhere that gives the software, when it starts up, all the information that's needed to start up. So this header information for most cryptographic or for most full disk encryption products is usually in the open, so you can look at it. In terms of, like, if you look at on the disk, you can see the bits. If you know how to make sense of them, you can read them. TrueCrypt is sort of different, as in it has this volume header also encrypted. And it's stored in place in the system partition, and it's 512 bytes in size, and we'll see in a minute why this is important. So as I said, the header is encrypted. There is a magic string, true, which is also encrypted, and if you provide your password to TrueCrypt on boot to the pre-boot environment, then it tries to decrypt the header, and if it does find then the magic string true upon decryption, then it knows that the key is right with a fairly high probability and goes on. For TrueCrypt, you can also use file-based volumes. So these are files that are then opened and made to look like a disk. And these have additional headers. And they're significantly bigger because they implement other stuff. There's a backup header, which is also not present when you encrypt the disk with TrueCrypt. The interesting part here is that the encryption key for this backup header is derived from a different salt. So if there's something wrong with the front end, the first sector, then you can also always go back to the backup header and use it. again, omitted for in-place encryption. So if you look at a disk, you have the sector 0 over here. Let's just call this the first sector, which is your MBR, your master boot record. It contains the stuff needed to boot, to initially boot the system, and partition table and everything else. Then for some historic reasons, there's a couple of sectors that are unused. And then there's the operating system. And maybe you have a second partition that starts at some sector X and goes to the end of this system, and it's an unused system, unused partition. And this would be the setup you would have to have for TrueCrypt to use hidden volume. What you do is you install TrueCrypt, tell it to install to encrypt the system. For a hidden operating system, what it does is it encrypts your system. It uses this partition, encrypts it, and you're supposed to put some decoy data on here. And then in the last step, it creates a little hidden segment in here, which is your hidden operating system. So with this feature, you can provide password A to the boot environment, and this operating system starts, and you'll see this data. You provided password B, and this operating system starts right here, and you see this data. And the operating system, the TrueCrypt driver, actually implements all the logic so that when you run this operating system right here to the system, it looks like it's running from the first partition. So Windows doesn't know anything, well, major Windows doesn't know anything about the encryption at that point either. So another interesting part is the in-place encryption. So again, the start-out layout. You install TrueCrypt. What it does is it allows you to encrypt the first partition, because every byte you encrypt on a hard disk takes up that amount of bytes on in encrypted form. So you don't win or lose any data, sort of, in terms of like what size it is. So if this is your file system, you encrypt it, you use that same amount of size, but you need to store the TrueCrypt header somewhere, and TrueCrypt actually prepends it to the before the partition. So because there's some unused space over here, it can do it here, but with the second partition, there's no unused space in here, so it cannot convert the second partition on the fly because it doesn't have any room for the header. If you have, for whatever reason, some extra space in here, if your partition 1 ends, then there's some slack, and then your partition 2 starts, then you could also encrypt the second partition. Although I don't really know if TrueCrypt would really identify that and work correctly. This cryptor is a little bit different in that respect. It actually shrinks the file system a little bit and places the TrueCrypt header inside the partition. So I would argue it's even a little bit more compliant with the TrueCrypt specifications than TrueCrypt itself. So what it does is it inserts the header here and then pretty much shifts every block back one when it's being encrypted. So the encryption driver from TrueCrypt knows if it's encrypted, it needs to shift it over. If it's not being encrypted yet, it knows this is the place where I start from. And this is also the reason why this cryptor encrypts the disk in the initial encryption from the back to the front. And the benefit is you can have a second encrypted partition on there. My last point is open source feature wish list. Of course, TrueCrypt compatible user and key management. So I would like to see TrueCrypt, the body, TrueCrypt, the organization, address this lack of feature at some point. And maybe they can do it by extending the current specifications, or they just add on some other specifications that allow you to lay off your user and key management data outside of the actual TrueCrypt header. So that way you could stay backwards compatible and also allow for user and key management to take place. Pre-boot authentication. I would like to see some additional implementation where the pre-boot authentication environment is stored. Right now, it might be stored in some slack space on the disk, like the unused sectors up front. There's other ways you can think about it. Maybe you put it in some hidden sectors on the disk, or you maintain the pre-boot authentication environment in a file that's as the only piece of information on a disk is not being encrypted. Cryptographic key storage, TPM support, high security modules, network booting, so anything that's interesting to push the key out of the system, but to allow automation like for a server environment. Protection against cold boot attacks. I would say this is because I'm running down low on time. Well, so cold boot attacks pretty much you're vulnerable to now. There are ways that you could theoretically right now protect against it by keeping the key material not in memory but inside the CPU, make it thus harder to get to. Cache lines, specific registers that if you can get your operating system to not otherwise use these registers may be a point. I/O ports, maybe. Makes it slow, but could be an approach. So there's various ways that can be looked at, and I would like to see some effort made in that direction. So there's a workshop tomorrow from 7 until 8 in A3. I believe the room holds about 20, 30 people maybe. So if you're interested, show up early, and there's no agenda just yet. I'm willing to work with you on whatever sort of topic or questions you have. So this is it. Thank you for your attention.
Although there's maybe a wish list of free software, open source software, do you really think it's a good idea to use or to recommend to customers cryptographic systems or products that are closed source or proprietary, because you have even not a chance to prove whether there are proof or whether there's a backdoor?
Right. So that's if the open source community can add enterprise support to these projects, whether TrueCrypt, Descrypt, or whatever else, then you have a foot in the door that that corporations will just gladly take. Right now, it's just not acceptable to them.
I'm just taking the opportunity to make a question to the audience. It's because I have an older hard disk with loop IIS encrypted, and I forgot a part of the passphrase. So if by chance anyone, I mean I have most part of it for sure, but if by chance someone wants to try a hack on it, then please talk to me. Thanks.
All right. All right. I have also one more, since I forgot about the additional questions. Where's the guy in the back that raised his hand? Is that you? Did you raise your hand? There you go.
Thank you.
You're welcome.
Maybe I have one question. I mean, TrueCrypt is free software and open source software.
Right.
So basically I can look inside the source code.
Right.
But since I'm not able to understand what is inside the source code, who can tell me, is it really safe? And I heard that some security experts like Bruce Schneier, etc., had a look into the source code and said, well, it's a pretty mess. So what's your opinion about that?
I said earlier that I have some issues with the TrueCrypt internals. And this is my point, is their source code is C++ and assembly. And while C++ is an interesting language, it's not really a good choice for that sort of environment. And they have just issues in their source code. Without me being able to say, okay, this is wrong, I just, when I look at the source code, I sort of don't like it. And honestly, Descriptor, there are parts that also feel that way. So there's much room for improvements.
Okay, here. Just like to say that with de-encrypt, if you skip locks, you can actually do it. You can do it offline, but you can't DD. If you DD the source from the device then to the de-encrypt, you can actually do it.
This is what I meant with workarounds.
Okay.
You just cannot, click a button and then.
And it's not very safe either, because if you lose the power, you have no idea where you were and where you can start off again. So it's not very safe, but it can be done.
Right.
Having encrypted my disk, in case of system or disk failure, how safe is my data?
Very. No. You mean how likely are you to retrieve your data? I would say that depends on the quality of the product you choose and the specific type of failure. So if, for example, your TrueCrypt, your disk fails and all the TrueCrypt headers are gone, then you would have pretty much no way to get your data back because you like those headers. TrueCrypt actually has a useful but otherwise annoying feature that helps target this. They force you, when you initialize your disk, when you encrypt your disk, to create a CD with your backup header. So they force you to make this, and it's annoying because even if you want to just test encrypt the VMware or whatever, you have to somehow manage to write a disk. But for just that purpose, it's a good way. If you have individual data sectors that are failing, it behaves pretty much just like a regular disk without encryption, those sectors failing.
I don't understand the advantage of storing the encryption key in the TPM chip instead of storing on the hard drive.
Okay. So pretty much the benefit is that the TPM chip implements some access logic. So when the key is stored on a disk, protected by a password, you can brute force attack that key. When you have it stored in the TPM chip will self-destruct after 3, 10, whatever wrong inputs. And because it's a hardware system, it's harder to copy. I'm not saying it's impossible to maybe scrape off the top and whatever ways to extract the key, but it's harder than just taking a copy of a disk and then brute forcing it. Okay. Thank you again.